So whenever you took algebra, at some point, hopefully, along the way, you learned that you need the same number of equations as you have unknowns. So, if you have x, y, and z unknowns, then you need 3 equations. And if you had, a, b, c, d, and e, then you'd need 5 equations. And there's a similar property for statics, which is essentially that you always need a certain number of equations in order to solve for all the missing stuff that you've got. If you want to establish that something's in equilibrium in 2D, you have to establish that the sum of forces in the x direction is 0. You have to establish that the sum of forces in the y direction is 0. And you have to establish that the sum of the moments about any particular point, O, is 0. Okay? Now, there are actually some ways around this. I never really solved the problem by thinking, okay, do I have all the equations I need? I just kept coming up with equations until I had them. But essentially what you need to know is you gotta have at least 3. There's all kinds of ways we could talk about it. You could say, if I've got points A, say B and C, if I've got some forces coming in here, however they are, I could say, well, I at least, basically where I'm getting to this is that at any point you need at least one moment equation. You actually can get away with having only one or even not having any force equations, but what you're going to find out is that if you have a certain number of equations, if you only have one of the force equations, then there are ways that say A and B would have to be related. If you have moments about there, then you can only use this force. You have moments about here, you can only use this other force. But honestly, rather than even discussing it that much or running into it, I would just say, write down everything you know, cross your fingers, it'll probably work out. But you do have to have at least one moment equation, because if you just use forces, you only have 2. When you're doing things in 2D, you need at least 3 equations to be able to solve your equilibrium problems. I do want to take a little bit of time to talk about how you can simplify 2 and 3 force members. Or not even really simplify, I'll just talk about 2 and 3 force members. And by that, I mean, say you have something like this, a little curve, something or other. If you've got a force like this, and say a force like this, let me try to make it really crazy. A force like this, these 2 forces can never be in equilibrium. This will never be in equilibrium. It will also never be in equilibrium if you have some kind of a, whatever this is supposed to even be, a telephone. If these forces are parallel, but they don't line up. You see how that'll never be in equilibrium? This one's always going to want to spin this way. This one here is always going to want to spin, I don't know, that way. Yeah, that one's always going to want to spin that way. The only way that these can be in equilibrium is if you have these forces. If you have a 2-force member, the only way it can be in equilibrium is that they both have to be along that line of action, because this way they produce no moment. So really what I'm saying is there's no rotation. So they must and can be, I'll just say can be. This also applies to dynamics. So these can be in equilibrium. So if you ever notice yourself having a structure that has 2 forces on it, it has to be in equilibrium. And in statics, these have to be same magnitude and then opposite direction. Like that. Same magnitude, opposite direction. So that's your 2-force member bit. Now for the 3-force member, there's actually a little bit more to do with that. Okay? Now for this to be in equilibrium, come back. So this would make sense if we actually worked it all out. You can either have all the forces could be parallel to each other, so they could vary in magnitude. Why I drew that, because I'm talking about 3 force members. You know, I could have something like this. I could have this guy over here. I could have this guy over here. But it's not too hard to imagine that as I move these forces around, I could even move him to be on the top. Come here. If I'm sufficiently careful in my placement so that I don't produce a moment, I could see that these could be in equilibrium. Now, if I pull him over here, and I pull, well, I guess I could do that too. You can, as long as these guys are parallel, you're okay. The way that we actually say this formally is that they intersect at infinity, right? Because they're parallel. It's one of those math things. So this is actually equilibrium is okay here. If you don't have lines that are parallel, it's okay as long as they intersect. So if I have something like this, let's see, and this guy's, say, pushing here, and this guy's, say, pushing here. If you can draw along their line of action, and he's actually in the position where they're along the line of action, then this is also in equilibrium if they all intersect. So this is where the links are important. So if they all intersect, then they are in equilibrium. So for example, if I wanted to place another force, say I had the same thing with this guy kind of going here and this guy kind of going here, if this force was here, see how they don't line up? That means that this is not in equilibrium. So this one's okay, this one's not okay. Not in equilibrium. And we could go ahead and prove this algebraically. I just don't think you really want to. So again, the whole idea is that these up here, they do intersect because they intersect at infinity. These intersect here. If you have a 3-force member, the only way it can be in equilibrium is if somehow those forces intersect. So this force has to be placed here in order for it to work. If it's here, anywhere, the only place that it can work is there. And that's in order to maintain a net moment of 0 and a net force of 0.